Okay, good. Can you all see the board?
Yes, sir.
Okay, all right. Uh, I think I couldn't remember exactly yesterday or day before yesterday. I have sent an tutorial to your batch rep. I don't know whether you all have received it.
Yes, sir.
Right. So you can try all these three sums. Today or tomorrow, I will send another set for the other group and so on. Right? Okay. You all can try that. If you all have any doubt after doing that, you can ask me. Not now. After solving all the sums, you can ask the questions. Right? All right? Right. Today we will start with a kind of testing. Can you remember we took three assumptions under the Pool T test. One of the assumption is homogeneity of variance, right? One of the assumption is homogeneity of variance. Actually, the assumptions shouldn't be tested. Assumptions, whatever the assumptions that we are taking shouldn't be tested, but in this case, we do test the assumption of the homogeneity of variance. Can you remember homogeneity of variance? We set homogeneity of variance. We assume sigma 1 square is equal to sigma 2 square. So that means the variance of the first population is equal to the variance of the second population. So that is the assumption that we take in a Pool T test. But as I said, there is a need of testing this assumption. Why? Because if the variance are not equal, then we'll have to approach a little different way to get the test statistics. The calculation of test statistics is slightly different if the variance are not equal. For that purpose, first we'll have to look at, in general, whether it satisfies this assumption, homogeneity of variance, right? Now we are going to look at how to do the test. Again, when you talk about test, it is comprised of all these 4 steps. Don't forget that. What are those 4 steps? What are those 4 steps? Formulation of hypothesis. So what is my null alternative hypothesis? My null hypothesis, what I am going to test, right? So I'll put the title, testing for homogeneity of variance. So my first step is formulation of null and the alternative hypothesis. So that is my null hypothesis. What is the alternative hypothesis? This is not equal to sigma 1 square is not equal to sigma 2 square. So this is not equal to that. That's all. We don't want to say or see whether sigma 1 square is higher than sigma 2 square. That is not necessary here, whether the variance are equal or not. That's all. Right. That is your first step. The test statistics, here we are using F test. FC, F calculated value, because we are going to, this is the ratio between sigma 1 square and sigma 2 square, the one we are going to test it. So this ratio between sigma 1 square and sigma 2 square is distributed not normally here. It is a F distribution. Because here, this is the distribution of one normal distribution. This is coming from one normal distribution. This is coming from another normal distribution, right? So when you divide one normal distribution by another normal distribution, the resultant distribution will not be a normal distribution. The resultant distribution is not a normal distribution if a normal distribution divided by another normal distribution. Therefore, this distributed like F distribution. We have talked about F distribution. Can you remember? It is a skewed distribution to right. Starting value is 0 and it goes up to plus infinity. So that is the features of the F distribution. Starting with 0 and goes up to infinity. And it is a right skewed distribution. We learn about this, right? So now we are going to use this distribution to come to our result. So the calculated value is simply the ratio between the variance, sigma 1 square divided by sigma 2 square. Any questions? So that is about the ratio between sigma 1 square divided by sigma 2 square, which is called as F calculated value. Now the third step is decision making process, right? The decision making process, if our calculated value is greater than the table value, then we reject our null hypothesis. So in other terms, this is the rejection region in a F distribution. This is non-rejected region. That is the non-rejecting region. Rejecting region and non-rejecting region. So if our calculated value fall into the rejecting region, if our calculated value falls into the rejecting region, then we do reject our null hypothesis. Then we do reject our null hypothesis. So that is what we said, decision making process. If calculated value is greater than the table value, we reject it. If we reject, what is the results? What is the conclusion? If we reject, what is the conclusion? As an example, if we reject, the conclusion is sigma 1 square is not equal to sigma 2 square. So the variants are different. If the variants are different, we cannot apply the same statistics or test statistics that we have followed with the pool variance, etc., that we have seen last week. So that same test statistics cannot be practiced. So we'll have to look at it a different calculation method. Actually, the degrees of freedom will differ. We are not going to discuss about that. We assume always there's an equal variance. For example, if you do this kind of exercise in any kind of statistical software, it will give the results for two different conditions. One is when the variance are assumed as equal, the one results. When the variants are not assumed as equal, another results will be given. So equal variance, not equal variance. So that is how it comes in the softwares, if you submit programming softwares, right? So if you reject your null hypothesis, we cannot do it, right? Can we take the same example as we did last time? So here, as you all know, since we don't have any sigma 1 square or sigma 2 square, we take the estimate of those S1 square divided by S2 square. So that is the estimate that we take. Right, now we can refer to the example which we did last week. Can you recall in a pool T test where we have come across with the variance of these two? Can you remember? What is the variance of first sample and the variance of second sample? What is the variance of first sample and second sample?
1 is 21.56.
Yeah. Second one?
15.28.
15.28. Right. Okay, we will take this example and try to understand. So my null hypothesis and the alternative, as usual, sigma 1 square is equal to sigma 2 square. Sigma 1 square not equal sigma 2 square. The second step is the calculated value, that is S1 square divided by S2 square. What is the answer for that? S1 square, let's say 21.56. S2 square is 15.28. What is the calculated value then? Somebody tell me what is the calculated value?
$1.410.
Right, 1.41. Now to look at the table value, we need 2 degrees of freedom, N1 minus 1 degrees of freedom and N2 minus 1 degrees of freedom. We need 2 degrees of freedom. N1 minus degrees of freedom and N2 minus degrees of freedom. Take the table and go to the F table. I think, yeah, F table, you have the F table. Look at it. Look at the title. It says the table, the F table. So here in the F table, it has given 2 entries for a given degrees of freedom. The first entry is for alpha 0.05, second entry alpha 0.01. So here we assume our alpha is 0.05. Even if your alpha is not given, you can assume your alpha as 0.05. Right. Now, what is the numerator's degrees of freedom? So, N1 minus 1 is the numerator degrees of freedom of first sample. Numerator degrees of freedom. This is denominator degrees of freedom. N2 minus 1 is denominator degrees of freedom. Numerator degrees of freedom of first sample, degrees of freedom of second sample, which is denominator degrees of freedom. So that is how you get the degrees of freedom. What are the degrees of freedom for numerator and the denominator? First sample and the second sample?
9.
Yeah, both have 9 because they have equal sample size. So in this table, row wise, the first row gives the numerator degrees of freedom. You can write down numerator degrees of freedom. In the first column, it is giving the denominator degrees of freedom. So my numerator degrees of freedom 9, denominator degrees of freedom also 9. So look at the value for 9 and 9 for alpha 0.05. So what is the answer?
3.18.
3.18. So this is my table value. This is my table value. Right. Let's go to the decision making process.
Excuse me, sir.
Yeah.
So there are 2 values, so how to take that one?
Yeah, that is what I said in the table at the beginning. Read the third line in the table. Look at the third line. In the third line, it says the first digit is giving for alpha 0.05. The second digit is given for alpha 0.01. In our example, we are considering alpha as 0.05. Okay, is it clear? So, is it clear?
Yes, sir. Okay, thank you.
Yeah, it is for each cell you have two values. One is for 0.05 alpha, the other one is 0.01 alpha. But in this example, we have alpha 0.05. So look at the first digit. If I say assume the alpha as 0.01, then we'll have to look at for the second value, right? Okay, right. Now this is my value. So here, if I demarcate my critical value or the table value, 3.18 means that is this value, 3.18 in our example. Now you see whether this calculated value is falling in the rejecting region or non-rejecting region. Tell me.
Non-rejecting region.
Non-rejecting region. It is falling somewhere there. So that means in our case, our calculated value is actually less than the table value. Table value is higher. Therefore, do not reject hypothesis. So in other terms, accept our null hypothesis. Do not reject our null hypothesis. Accept our null hypothesis. So if you accept our null hypothesis, what do you mean? What is the assumption? Is the assumption is acceptable or not acceptable? If the assumption is valid or not valid?
Not valid.
Why?
Valid, sir.
Valid, yes, because we are accepting our null hypothesis. What does null hypothesis? Null hypothesis says the variants are equal. So our assumption is valid. So we can proceed with our normal way of calculation. Clear? So this is an example how to test it. Suppose if I have a value here, suppose if I have a value 3.4841. Suppose if I have a value ratio between the variance is 3.41. Now what is the problem? Now the calculated value is greater than the table value. Therefore, we may reject our null hypothesis. If you reject our null hypothesis, the procedure that we have taken is cannot be processed. Why? Because the assumption of variance cannot be assumed further. That means we are rejecting our null hypothesis, accepting our alternative hypothesis, assuming that there is a difference among these two variants. If there are a difference among these two variants, then we cannot go through the same process or procedure. Is it clear?
Sir, sir,
Yeah.
if calculated value is less than table value, that is
Non-rejecting null hypothesis. Here you see as an example, in another example, if I get a calculated value which is higher than the table value. You get the point? If it is higher than that, then we reject our null hypothesis. So the homogeneity of variance cannot be further assumed. Right? So we'll have to proceed with another procedure. Is it clear? So if the calculated value is smaller than the table value, then we can assume homogeneity is prevalence. So homogeneity is existing, right? Because of this rejecting and non-rejecting concept. Is it okay? Right? Yes or no? Can I proceed to other section? Yomi, did you understand?
yes, sir.
Okay. How about others? How about others? Kasuni? How
Yes,
about
sir.
Anand? Yeah. Did you understand, Kasuni?
Yes, sir.
Okay. Any questions, anyone? All right. Now we will look at, can you remember last time we mentioned in the two sample, there are two cases. One is independent case, the samples, two populations, independent cases. There are cases, dependent cases. What do you mean by dependent? Right? Look at this example. So, dependent sample, t-test, two sample dependent t-test is called as paired t-test. Right? It's called as paired t-test. Paired t-test. Right? Just to start with the paired t-test, few examples. What do you mean by pair? In earlier case, we have two groups of population. They are independent, totally. Their responses are independent. But here it is dependent. Look at, I'm taking 6 cows or 8 cows. Same breed, same age, same parity cows. Right? I'm taking 8 cows with the same breed, same age, same parity cows. Now I have a new hormone, right? I have a new hormone which I am going to give it to the cows to see whether these hormones have some increase in yield or the milk yield. So we are measuring the milk yield, right? So by giving this hormone, whether this hormone induce more milk from the cow, as an example. So this may be injection or maybe fed with feed, right? So what I'm doing is, right, before giving the treatment, so my treatment is giving the hormone. The same level of hormone will be given to all 8 animals, right? But now we want to see whether this hormone has an effect in terms of increasing the yield. For that, what I'm going to do is, I'm going to measure the initial milk yield. Let's say today, what is the daily milk yield of each of these 8 cows, right? So let's say cow 1, cow 2, cow 3, and so on, up to cow 8. The milk yield right? Milk yield, right? Before the treatment. Right? That means I am going to measure the milk yield of each cow on a daily basis, average, right? Before giving the treatment. So what is the treatment? It is a kind of hormone that I am going to give it to the animals, expecting these hormones are inducing more milk yield. So now I have information. Before giving the treatment, I am measuring the milk yield. So after measuring the milk yield, now I am giving the hormone. I am giving the hormone. So after giving the hormone, can you take the milk yield on the following day? No, we'll have to give the hormone for 2-3 days continuously. Then after, let's say 1 week, we do the measurement again from the same cup. So now, again, I'm measuring the milk yield after 1 week after the treatment. One week after the treatment. I'm measuring the milk yield again 1 week after giving this hormone dose. Is it clear? Now I am measuring the average milk yield of all these cows separately. Right. Now, can you tell about, this is one group of population. That means the data which is coming after the treatment is one group of population. The data coming before the treatment is another group of population. Now tell me, are these populations are independent or dependent? These data are dependent or independent? Can somebody tell me? Are these data are dependent or independent? Anyone? Piomi? Tilini?
Dependent.
Yeah, it is dependent. Why? Because you see the second reading is totally dependent on the first reading of a particular cow. Why? It is because of human beings, metabolism. In this case, the metabolisms are different from cow to cow. Best example is, let's say, 5 of your batchmates go and sit in the canteen. Are you all getting the same, maybe you will be getting the same amount of food from the canteen, same quantity, same nutritional value. But if you look at the weight increment, maybe different from person to person. That is because totally metabolism, right? As an example. So this population is totally dependent on this population, initial value. So this final value actually is dependent on the initial value. So this is called as paired. Look at here, this is paired. These data are paired. Similarly, these data are paired. These data are paired, and so on. So this is called as paired t-test, even though we have two populations, but these two populations are dependent. Right, another example. Now we want to evaluate the livelihood of farmers, right? You might have heard about a lot of projects implemented by government. Let's say Divya Naguma, Gam Naguma, so many projects. Now we want to see whether these projects is a really worth project, whether the project is success project, whether the project has really increased the income of the farmers or livelihood of the farmers. Right? We can test it using this. For example, let's say I have farmers, 1, 2, 3, up to any number of farmers from a particular, before the project, right? Before the project, I measure the income of the farmers. I get the income, monthly income of the farmers, of 10 farmers before the project. Right? Maybe we are helping the farmers, right? of using different projects. So before the project, we get the income, their income, average income monthly of each of farmers. Now we are giving some subsidies or some kind of help to the farmers to see, or to our expectation to see whether they are well off in livelihood in the future, maybe after 1 year. So after 1 year, after giving maybe subsidy like seed paddy or whatever inputs you give it to the farmers, after 1 year, you go 1 year or 1.5 years. At the end of the project, you go and again measure the same group of farmers for their income, monthly income. So this is after. So you get that information from each farmers. Now you see, this increment is proportion to the farmer of one who had the income, let's say X at the beginning. So these two data are coupled, or in another term, it is called as pair. Okay. So now we can evaluate whether this project has an effect on increasing the income of farmers. That we can test. You see, that we can test. So here it is called as dependency. There is a dependency between these two populations. Right? Any questions? Any questions? Do you need any more explanation on these two examples? Paired. So these called as paired situation. Even though it's look like two population, these two populations are depend on each other. So this is called as paired t-test. If you apply the t-test on this occasion, it is called as paired t-test. Any questions? Sahara, any questions?
Sir.
Yeah. I don't hear any Sahara.
No, sir. No any question.
Okay. Any others? Any questions? Do you need more example on this paired? Or is it enough? Then we will go to some calculation. Yeah. Anyone? No response. Right. Now, one of the biggest assumption is independence. In our t-test, one of the biggest assumption is independency. Now we have two populations. Both populations are depend on each other. Now we cannot directly do any test. Right? We cannot directly do any test. Therefore, we'll have to bring this information to a independent setup, independent population. So how we can get the independent population is, so if we assume before treatment we have some value of milk yield as an example, after the treatment, after giving the hormone, there is a milk yield. Normally, suppose if you assume that there is an effect of hormone in milk yield, what is the value? What can you say about these two values? Which value is higher in general? Is it before milk yield or after milk yield? That is what we want to test it. Which value is higher? Anyone? Yeah, after milk yield is higher than the before, because we assume that this particular hormone is going to increase the milk yield. So now we want to get the difference between these two. So the difference is actually after minus before. After minus before. So in other terms, difference we write it as DI, the difference. So the difference DI in this example is after minus before. Right? I have another example. Look at it. Now, one company is there. Typist there. One particular company is there. Typist. 10 typists in that company, let's say. Now, I'm going to give a training to these typists. We are going to give a training to these typists to see whether this training has effective in terms of typing. So before training and after training. So what I'm going to do is, let's say these are the typists, 1, 2, 3. There are 10 typists. Now I'm going to give a particular document, let's say one-page document. One-page document to type it and record the time. Record the time. Is it clear? Before the training, I give a one-page document, which is already same to all 10 typists. It has been given. Now they are typing. Once they finish the typing, I am recording the time. So the time before, right? Before giving the training, the time taken. The time taken in, let's say, minute or minute. It is in minute, for example. The time has been recorded. I have given one-page document. Everybody got the same document, one-page document, and see how the difference is. Now I'm giving a particular training for typing. Typing or any work, right? I'm taking an example, typing. So after giving the training, again I'm giving the same page that has been typed earlier to see the time period taken for typing. Is it clear? So they are given again the same piece of document to do the typing. Now we are recording after the training. This is before the training, this is after the training. Time taken, I will put it as TT in minute. Now tell me, if the training is said to be effective, if the training to be said effective, what can you say about these time differences? Which one is higher, which one is lower?
Lower time in after training.
Lower time is after training, right? Lower time after training. That reflects that there is a effectiveness in training. Now if I take the difference, how do I take the difference? In this example, how do I take the difference? Is it after minus before or before minus after?
Before minus
Before
after.
minus after.
Which one is higher in general?
Before.
Before is higher compared to after. So here I can say before minus after. You see the difference where we are using that. You'll have to think always, because we are not going to teach you how to come up with the difference, whether before minus after or after minus before. So depend on the situation, you have to react. So in this case, after minus before, definitely after milk yield is higher, slightly higher compared to before. In this case, after is lower compared to before. So you see, when you take the difference, you have to have some logic behind. Is it clear? Right. So that is why I said don't follow the rule always after minus before. It can be before minus afterwards to take the difference. Right? Clear? For example, I'm taking cholesterol, for example. I'm taking 10 cholesterol patients and giving a particular tablet. So before giving the tablet, we are measuring the cholesterol level of each person. Then we are giving the tablet and measuring the cholesterol level. So in this case, what do you think? After minus before or before minus after? Which is ideal? Cholesterol patients? What do you think? We are giving some tablet. After giving the tablet, let's say after 1 month, we are measuring it again. So which is better, before minus after or after minus before?
Before minus after.
Before minus after. Is that correct? Yes, the value is higher. Before is higher because before getting the tablet, usually the value is high. The cholesterol value is high. So likewise, we'll have to think about it. Right? Okay. Right. So these are some of the examples, before minus after. Right. Now, earlier we had two dependent population. Now we have taken the differences. If you look at this population, this is the population that we are going to analyze or do the analysis of t-test. Now this population is totally independent. We are not going to do anything with that population. So this dependent population has been brought down into one independent population. So this we are going to do the analysis. So this is same as the previous analysis. What is this? Is one sample case. Earlier it was two sample, dependent sample. Now we have brought into one independent sample. Now we can do the analysis here. So usually my hypothesis, null and the alternative. I will simply put mu d. Mu d is equal 0. Mu d mean difference. Mean difference. Mu d is equal 0. The alternative is mu d not equal 0. For example, cholesterol case. For example, cholesterol case. Right? Before giving the medicine, I took the cholesterol. After giving the medicine, I took the cholesterol level. Now we had the difference. Somebody already said before minus after. Before minus after. How can we formulate our null hypothesis and the alternative hypothesis for cholesterol case? Can somebody tell me? Null is an easier one. What about the alternative one? I say before medicine, cholesterol level before medicine, after medicine. before medicine, after medicine, first person, second person. Right. What is the null and the alternative possible? Here it is the different. Difference is actually after, sorry, before minus after. The difference is before minus after. Yeah. Tell me, what is my null hypothesis? In this example, my null hypothesis is mu d is equal 0. I ask you to test whether this medicine is reducing the cholesterol level. That is my question. My question is, test whether this medicine is reducing the cholesterol level. Test whether this particular medicine is reducing the cholesterol level. So what is my null hypothesis? Null is same. When you say the difference is equal to 0 mean, what do you mean by no difference between these two, before and the after? Before and the after, no difference mean no effect by the medicine. So the cholesterol level before taking medicine and after taking medicine having the same level. So that is what we call as the difference, isn't it? If the difference is, for example, if the difference is 0, what does it mean? No effect by the medicine. Right. Similarly here, mu d is equal 0. What about alternative? Mu d is it one tail or two tail, first of all? So this is a two tail situation. But sometimes I can ask, test whether this particular medicine is reducing the cholesterol level. Somebody has given. It's not B minus B minus A. Oh, that is not equal to 0, doesn't matter. Because I want to say this medicine is effective in terms of reducing cholesterol. That is what my decision has to be. So not equal mean two things. When you say not equal, mu d can be greater than 0, mu d can be less than 0. So which one would you choose? If I say test whether this medicine is good for cholesterol, or this medicine is reducing the level of cholesterol. Is it mu d is greater than 0 in this example? You have B minus before minus after. Anyone? Yes, because mu d should be greater than 0, isn't it? For example, it should have some value, positive value. Some positive value. Then if it has a positive value, that means before minus after is better in terms of cholesterol, low cholesterol, right? So we can say mu d is greater than 0. This is how we can test it, the example. So now it is a one sample situation, but it is a right tail testing. You see, that is how we can form it. So I will give an example, then we will proceed. Right, now I have the question.
Yes, teacher.
Yeah.
Our assumption is check the medicine if cure or not.
No. Medicine, whether this, by taking this medicine, whether cholesterol has gone down or not. Cholesterol level has gone down or not.
Okay.
There is no point of taking this medicine. Do you understand? We want to test whether by taking this medicine, whether the cholesterol level has gone down. right?
Thank
That
you.
is what we are going to test it. So that is mu d. I mean, if you accept null, taking medicine is no worth, because before and after the value is more or less same. No difference between these two values, right? The difference is equal to 0. But here the difference is more than 0. That means before has higher value than after. For example, if I turn this other way, that is also possible. If I can do the calculation other way, after minus before, what do you expect if the medicine to be effective? Here we have minus values, not plus values. So in that case, my null and the alternative are this alternative mu d less than 0. So you'll have to be careful which minus which one. So now this is after minus before. Let's say we have some values. Let's say this is 100, this is 95 as an example. So after minus before is minus 5. In earlier case, before minus after. If it is before minus after, this is plus 5. You see the sign. So that is why you have to be careful which alternative coming with which deviation, taking the differences. Right? Okay, we will do an example. Milk yield, again milk yield, example of a milk yield. Milk yield of how many cows? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cows. Milk yield of 10 cows. Right? Milk yield of 10 cows. Before and the after, giving a particular hormone is recorded. Before, after. The values are 20, 21, 19. This is in liter, let's say 18, 20, 19.5, 22, 20, 18, 21, 23, 20.5, 17.5, 22, 21, 23, 22, 20, 19.5. So this goes as pairs always. These values goes as pairs. Right? Test. Write down the question. Test whether the hormone increase the milk yield of cow. Average milk yield of cows. Test whether the hormone increase the average milk yield of cow. So how to do the test? Right? First thing, mu d is the mean difference. Mu d is equal to 0. The other one is mu d depend on which minus which one, right? Here, if I take the, let's say, after minus before, I'm taking after minus before. If you take after minus before, so usually after value is high, right? So we could say, if I have a positive value, then we could say there is an effect by the hormone on increase of milk yield. Right? Right. Can you take all the values here? We have to take all the values, positive, negative, separately. I mean, indicate it. So what is first value? +1. Second value, +2. Third value, +1.5. Fourth value, -0.5. Right? 2 plus 1.5, which is also plus. So take the +1, +2, +2, and +0.5. So these are the differences. Okay. So this is my null and alternative hypothesis. These are the differences. Now I want to have test statistics. Calculated value is depend on, it's like a one sample t-test, di bar, the mean of difference, minus the hypothesis value, divided by SD, standard deviation of the difference, divided by square root of. SDI means standard deviation of the differences. Standard deviation of differences. Right? Okay. Standard deviation of differences. So that is simply the one sample case. Can you find out the values? I need two information to further calculate. What are the information? Di bar. N is already there. What is N? I need all these information. N, di bar, it is the di bar mean, add all these value, divide by the number of mean, divide by number of sample. The third information I need is the standard deviation of the difference. Standard deviation of the difference. So these are the values. Now no more this value is applicable. Only take these values. Right? Only take that value. Any questions?
So,
Yeah.
absolute values.
Yeah, calculate and not absolute value. Here there is nothing called absolute value. Here all the values. We can't say absolute value because here we have negative and positive signs. So you do it as it is. So what is di bar? For example, this plus 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 plus. So what is the average value?
1.3.
1.3. Yes, that is good. So you add all the values in a normal way. Add all the values, you will end up with 1.3. What is the sample size? Sample size is 10. Can you calculate the standard deviation? Can you calculate the standard deviation? I will give 2 minutes. Calculate the standard deviation. Standard deviation of this sample, no? The difference. calculate the standard deviation?
Three 3.5.
Huh?
3.5.
No, standard deviation. I'm asking standard deviation. Don't go for the rest. First, standard deviation, calculate the standard deviation. What value you said? 3.5. Is that standard deviation or something else?
No. 0.38.
I'm getting a different answer. Try standard deviation. Huh? Standard deviation for all these values.
6.1.
Huh?
6.1.
No. It is less than 1, but
0.78.
0.78.
7. 8.
Yeah, that is closer, but I'm getting a value 0.82 because I did it using computer, so that it is giving accurate value. Standard deviation, I'm getting a value. Yeah, standard deviation never minus value. Huh? Something wrong with somebody. Huh? Don't say standard deviation never minus value. Huh? Then if you say standard deviation minus value, something wrong. Standard deviation, it will be always positive value. That is why we are squaring it. Can you remember the first lecture? We are calculating the variance, observed value minus the mean value, then square it, sums of square, because to avoid this minus value. Yeah, some value like I have a value, I'll put it there. 0.823. I'm getting a value something like that. Now can you try get the calculated value? Can you try and get the calculated value? So di is 1.3 minus hypothesis value testing is 0 divided by 0.823 divided by square root of n. What is the n? Square root of 10. So what is my calculated value? What is my calculated value? Anyone?
5.
Once again,
5 nearly 5.
5. How about others? Are you all getting the same value? Calculate value. 1.3 divided by this fraction. Yeah, let's assume 5. Somebody else also give the value. Calculated value is 5. So now what is the table value? Table value is n minus 1 degrees of freedom with alpha, because it is a one tail. Look at it, it is a one tail. So look at with the alpha, as usual, the alpha value is 0.05 and the degrees of freedom is 9. So take the table, T table, and look at the value. 0. This is a one tail. So how to look at the one tail in a table? How to look at the one tail in a table? You multiply by 2, right? So look at for value of 0.1 and with 9 degrees of freedom, 1.833. Value is 1.833. So if you look at the distribution, T distribution, we are talking about the right side. So this value is 1.833. So this is a rejecting region. This is non-rejecting region. That is non-rejecting region. So what is our conclusion? Look at this calculated value. Since our calculated value is greater than the table value, that is our decision-making process. Calculated value is greater, then reject on null hypothesis. So 5 is somewhere there, falling into rejecting region. Therefore, what is our conclusion? Our conclusion is, what is our conclusion? Anyone? We are rejecting our null hypothesis. We are accepting our alternative hypothesis. Now tell me in terms of writing with text. Anyone?
Average milk yield is not increased by using the hormone.
Average milk yield
Is not increasing
by, we are rejecting our null hypothesis. If you
increasing.
null hypothesis, what is we are accepting our alternative hypothesis. When you accept alternative hypothesis, there's evidence that the mean difference is more than 0. There's evidence that the mean difference is more than 0. So what do you mean by that? There's evidence that this particular hormone has increased the milk yield of cows. That's all. It is increasing the milk yield. That is what we are testing. If it is 0, if it is equal to 0, if we accept equal to 0, because this minus this, if this minus this is equal to 0, then no difference between these before and after. But this is greater than 0, so that we could say there's evidence that milk yield increased. Milk yield increased after treating with hormone. A particular hormone. If you have given the hormone name, you can say increased. Milk yield has increased. So that is the conclusion. Any questions on this? I'm not going to do any more examples on this. I will send some examples later on. Any questions on this? Anyone? Need any clarification on any of those All are silent. So everybody understood, right? Yes or no? Senori, are you around?
Yes, sir.
Yeah. Did you understood? Clear?
Understood.
Huh?
Yes, sir. Understood.
Yeah. Janali?
Yes, sir.
Yeah. How about you? Did you understood the problem?
Yes, sir.
Okay. Subaraj? Ask Subaraj.
Yes, sir.
Yeah.
Understood.
Okay, good. Uh, Mahajini?
Yes, sir. Yes, sir. Understood.
Okay, good. So if there is no question, I mean, anybody would like to ask any question on this example? So this is before and the after. Similar kind of before and after possible, right? Suppose let's say uh, we have factory operators, some factory operators, let's say machine operators, some machine operators for a particular company, right? So before they have been given any training, they have been given a task to fulfill and measuring the time taken to fulfill that particular task, right? The time taken to fulfill that particular task before the training. Then after the training, again you give the same task. See whether they have done the same job in a lesser time period. So that is actually the one which we want to evaluate, whether the training has effected or the training is effectively implemented in terms of improving the worker's skill. So that means worker skill mean it is reducing the time. So likewise, you can apply in several fields. Similarly, here we can go for confident interval. We can construct confident interval. Similarly, for this also we can construct confident interval, right? Let's say 95% confident interval. Di bar plus or minus, again the t alpha by 2 n minus 1 degrees of freedom into s di divided by square root of n. So this is we can have a confident interval as such. So is equal 1.3 plus or minus. What is the table value? What is the table value? 2 point. This is alpha. If it is alpha is equal 0.05, what is the table value? For degrees of freedom 9, 2 point?
262.
Yes. Right, 2.262 multiplied by this component. Can you tell me the answer? 1.3 plus or minus? What is the answer? Get the answer of this. What is the answer?
0.5889. 89.
Okay, so we will take it to the 3 digit. So this is 1.3 minus 0.589. So 1.3 plus 0.589. Get me the actual value. It is, what is the value here? 0.
0.71.
So 1.9, let's say 1.88, right? Right. What do you mean by how we can interpret this? How can we interpret this? The true mean difference between before milk yield and the after milk yield. That means before giving the hormone and after giving the hormone, the milk yield increase is this much. So we can say after giving hormone, we are 95% sure we are 95% sure that true milk average milk yield increased average milk increase or average milk yield increase is in between average milk yield increase is in between 0.7 to 1.9 liter right? And we can put this word somewhere. We are 95% sure that average milk yield increase after treating with hormone. So include a term after treating with hormone. We are 95% sure that the average milk yield increase after treatment with or after treating with hormone is in between 0.7 to 1.9 liter. Right? Okay? So you see, this information, we can put it in that way also. So the milk yield has increased after giving this hormone. On an average, milk yield has increased this much of liter. So that you are 95% certain, or 95% sure that milk yield is increased after giving the hormone. by 0.7 to 1.9 liters. Right? So this is how we can interpret that. Any questions? Any questions? Right. If not, we will continue with, I have the next section, which is with the PowerPoint presentation. So I will send this soon, copy of this, right? My next section will be on regression and correlation. Regression and correlation. Okay. Is Jeffrey around? Jeffrey, are you around? With the second rep, touch rep. Who is around, Jeffrey or somebody else?
Yes, sir. Comes with me.
Ah, right, okay. So, is Jeffrey is around? No, he's not participating, right? Any problem? Any problem with Jeffrey? I didn't see most of the time. Right, regression and correlation. That is the next topic. This is a slightly large topic. What is regression, first of all? Regression and correlation. First, we will understand what is regression. Regression, we try to develop a relationship, nature of the relationship. When you talk about nature of the relationship, let's say we have two variables, x and y. How these variables are distributed, for example, right? So I will use the board, that would be better. So when you talk about the nature of the relationship, when you talk about regression, the nature of the relationship, you see here the nature of the relationship is likewise, right? So nature of the relationship is linear. It is called as linear. Look at this nature of the relationship here. This is non-linear. You see, this is what we call as a linear relationship. This is a non-linear. So when you talk about linear, when x increases, y change at the same rate anywhere. Maybe y may increase, y may decrease. So it is a linear relationship. This is a non-linear relationship. So when you talk about this regression actually gives the information whether what is the nature of the relationship. This nature of the relationship can be linear relationship. This is what I have already shown you on the board. First one is linear, second one is non-linear relationship. When you talk about simple, we are considering only two variables, x and y variable. These two variables have specific name. called as X is called as independent variable or explanatory variable. Y is called as dependent variable or response variable. Right? So independent variable or explanatory variable, dependent variable or response variable. The process of predicting the Y variable using X. So this is what we are actually expecting. The main purpose of this kind of regression analysis is to predict the Y value using the X value. That is the expectation. Maybe sometimes you have learned in economics, for example, for this much of input, how much of output you can obtain. Maybe in agronomy, for this much of fertilizer application, how much yield that you can obtain. So this is called as the predicting the Y value. It tells you how this Y value changes as the function of X when the value of X changes, right? It is giving the change of Y in terms of as a function of X when X changes. Let's look at what are the types of relationships available, nature of the relationship. First one is called as, this is a relationship called as linear relationship, right? So this is, first one is a positive linear. When X increases, Y also increases. The second one is negative linear. When X increases, Y decreases. Right? Both are called as linear. This is non-linear. Example for non-linear, or sometimes it is also called as curve linear. Non-linear or curve linear. Let's look at what are the types of relationships available. First one, there are 5 types I'm going to describe. First one is called as exact linear relationship. That means all the points are lying exactly on the straight line. The data points follow the linearity. Normally, this is a man-made relationship. Naturally, you don't get this. For example, the relationship between hours and the minutes, right? If you take hours in y-axis, minutes in x-axis, definitely all the values are lying on the straight line. Because the relationship between hours and minutes, when you divide minutes by 60, it is giving the relationship of hours. So 1/60 into minutes, right? The second type, this is a man-made, exact linear relationship, which is a man-made. Second one is called as exact non-linear relationship. Have you seen a non-linear relationship like this? Nice curve, maybe in your A level, maybe in your chemistry, you might have seen this. For example, the Boyle's law, PV equal K, right? PV equal K. Yeah, Boyle's law, PV equal K. So this is typical. This is also a man-made relationship. Exact linear and exact non-linear relationships are man-made relationships, right? Now we are coming to the third one, which is called as non-exact linear relationship. Almost all the natural values on the earth are based on this relationship. So this is called as non-exact linear relationship, right? Non-exact linear relationship. The relationship is linear, but it is not exact. the relationship is linear, but it is not exact. Just a minute. I'm in a lecture. I will call you back later. All right, the relationship is linear, but not exact. Okay. So most of the data is in that format. Y is equal beta naught plus beta 1 x plus the error term. So we'll explain a little more on this in the upcoming chapters, right? So this particular relationship is actually explaining a few things. It's like y equal mx plus c, this line, right? So this is beta naught. This is the intercept, beta naught, and we have this beta 1, which is the one which is giving the slope. So if you have the slope, we can measure the, let's say this is the slope, we can measure delta y divided by delta x. So delta y divided by delta x will indicate the beta 1. Okay, the rate of change in y when there is a change in 1 unit of x. Right? The last one, this is called as error term. You may heard this is for the first time. The error term, actually, look at this points. Error term, let's say this is the straight line. I'm taking 1 point for explanation. So this deviation is given by the error term. How much deviation that particular point is from the predicted line. This is called as predicted line. We will come across later. So how this predicted line or the distance between the observed value and the predicted line is basically called as the error term that we will see later. All right. So this is the model for a non-exact linear relationship. The fourth one, intrinsically linear relationship. Intrinsically linear relationship. Actually, this graph is look like not linear. It is a non-linear. Right? This graph is look like a non-linear one. In the original form, there is no any linear relationship in the original form. Right? That is how it's look like this. But look at this equation, y equal exp, beta naught plus beta 1 x plus e, right? Now, by doing some transformation, we can bring this nonlinear term into linear form, right? Originally, it is nonlinear. However, it can be converted into linear form. Look at, if you take the natural log in both sides, ln y is equal beta naught plus beta 1 x plus e. So that can be written because natural logarithm, it is in the exponential. Now you see, in simple form, it is in the linear form, right? Y is in the log form or the natural log form, right? The rest is the normal way, right? So this is in terms of y equal mx plus c, the same as earlier. So now only the difference is we have converted this into
non-linear into linear form. So it is lny, which is indicating as the variable y and x. So there is a linear relationship between these two variables where y has been converted into ln form or the natural logarithmic form. Clear? The last one is called as true nonlinear relationship. Earlier one is intrinsically linear relationship that we can convert, which is originally on the nonlinear. But here, true nonlinear relationship, we cannot convert this into a linear form. So we cannot convert this into a linear form. Okay? We cannot convert this into linear form where y is equal beta naught x to the power beta 1 plus e. So we cannot convert this into linear form. Therefore, this is actually a true nonlinear form. Right? So the principle of simple linear regression can't be applied to true nonlinear relationship. Right, now let's look at what are the regression models available. We are not going to study all the models. We are going to study only the specific one. Regression model, we call it as simple and multiple. The difference is, if you have one explanatory variable, then we call it as simple. That means one x variable. More than one x variable, or 2 plus any number, 2 and 2 plus any number of explanatory variable, then it is called as multiple regression. Simple, linear. Under the simple, we have again linear and non-linear, we have already seen. In multiple also, we have two types, linear and non-linear. In this course, we are going to learn about only a linear regression model, which is a simple linear regression model. Right? So we are going to learn only the simple linear regression, only this portion. So it is called as simple linear regression. In this course, we are going to learn simple linear regression. Right? So what is simple linear regression? Again, the same slide which I have put forward earlier. Each of these terms have a meaning. The nature of the relationship is linear, so that is why we call it as linear. Nature of the relationship is linear, right? So that is why it is called as linear. And simple means we have only two variables. One is x variable, the other one is y variable. X variable is called as independent or explanatory variable. Y variable is called as response variable or dependent variable. As I pointed out earlier, we try to look at how we can predict the y value using the x value or x variable, predicting y variable using the x variable. Here we expect how the changes of y occurs as the function of x when x changes with values. All right? Right. Look at the linear equations. All right. Look at the linear equations. Y equal mx plus c. That is the equation of the straight line. What is this m? M is the slope. M is the slope. So slope is given as change in y divided by change in x. So that is given as slope. C is actually the intercept, y-intercept. So we can say y equal mx plus c. Y and x are variables in a simple form that you have learned. Linear relationship model we try to have the relationship between variables in a linear function. So this is the model that we are writing down for the linear regression. So you should remember each of these observed value, right? Suppose let's say I have values for y value, x value, right? So y1, y2, so likewise x1, x2, and so on. So in general term, we call it as yi value, xi value. So that is why you have yi value, each of these observation, y1 relate to x1. So similarly, xi value. So I can take any values in your progress of data. So yi is the observed value of the dependent variable. It is the observed value of the dependent variable at a given level of I. Right? Xi is the, again, value of independent variable at a given level of I. So y and x are the known factor for us that is coming from the data. All right? Then these are called as beta naught and beta 1 is called as parameters. What are those parameters? Beta naught is called as intercept parameters. This is one of the model parameters. So this is important parameter, one of the model parameter, which is intercept. The second model parameter is beta 1, which is said to be slope parameter. All right. So xi we have already seen. The last one is called as a random error at a given level of I. Random error at given level of I. So this is the basic simple linear regression model. So you should know this model and you should know how to explain these each and every component. Right? This is a constant value. Beta naught is a constant value. Beta 1 is also a constant value for a given data set or given situation. It is constant. Right. We have few assumptions. I will put all the assumptions together, then we will discuss. The first assumption, because when you do some parametric test, definitely we have to go through assumptions. The first assumption is the relationship between x and y. So we assume there is a relationship between x and y, which is a linear relationship. So for example, if you have the data as such, so look at this is the data. So there's a linear relationship. There's a linear relationship. So that is the first assumption that we do take. The second one, the observations are independent. Observations are independent. So you see here, we have y observation and x observation, different level of y observation and x observation. I will what is independency of the observation? Similar to the earlier case, the observations are independent. So we said yi, xi. So here we have values y1, y2, y3, y4, similarly x1, x2, x3, x4. These observations are independent. So here we have pair of observation, but between these pair, they are independent. So this is what we call as independent observation. Right? So the observations are independent. The variance of y at every value of x is the same. So that is another assumption. The variance of y is same at every level of x. So what do you mean by that? So when you talk about the variance of y at different level of x, let's take this x value. Let's say this x1, x2, x3. This is what. Let's take, I have some observation of x1 for the y, observation of x2, observations of x3. So these are the observations, right? If you look at the variance, distribution, which look like this. Again, it is showing a normal distribution, variance among the data. So here we have several data, here we have several data, here we have several data. You see, there's a linear increase on that. So that assumption at each x level, the variability is same. All right. So that is another assumption. The next assumption is the error is distributed normally, identically, and independently. So this is three words are very important: normally, identically, and independently. With a mean of 0, the error mean is 0, and this has to come here. With the mean of 0 and with the error variance, common error variance sigma square. You can see here, this is what I said. Normally, identically, and independently. Look at it. This is distributed normally. The error is distributed normally. Error variance is distributed normally. And identically. So all are same, identically. And independent. They are independent to each other. Identically, independently, and the normal. You can read all these. I will, right? Right. We'll stop with that. We will meet next time. Any questions? So this just we started with theory. Any questions?